Right, students. So today we'll discuss moment of inertia. Second part, I already discussed first part. No, please go through it first part. No, then come back to the second part. No, this second part is very important. So we'll see moment of inertia of the theorems. No, compulsory you can expect the questions based on this one. No? So there are two theorems are there, so which can be calculated moment of inertia of a different objects very easily by using this one. No? First of all, first theorem, very important, no? Most important, lot of application. From this theorem, compulsory question will be there. That is nothing but a parallel axis theorem. Parallel axis theorem. So why this is important? No, parallel axis theorem. Parallel axis theorem can be applicable for any type of objects, even one-dimensional objects now like a rod, two-dimensional objects like a ring, disc. Even it can be applicable for three-dimensional objects like a sphere, cube, cuboid, cylinder and on to this one. So parallel axis theorem can be applicable for any type of objects onto this, right? So that's why this is most important. No, what is this parallel axis theorem? We'll take one object. No, this is one object, right? For this object, for every object there will be a center of gravity will be there. Center of gravity where total weight is supposed to be concentrated onto this. Clear? This parallel axis theorem can be applicable for any type of devices. No, let us take this is one device. For this one, there will be a center of gravity will be there. Center of gravity. So right. So every object there will be a center of gravity where total weight of the object is supposed to be concentrated. So therefore, along this, right. So along the center of gravity, there is an axis passing through it. No. So this along this one, no, the moment of inertia. So we can write it as like a Ig. The axis passing through the center of gravity, the moment of inertia is Ig. Now you have to select any one of the axis, no, which is parallel to this, which is parallel to this. Therefore, if you are taking this is parallel to this one, no, therefore here we want to calculate the moment of inertia which is parallel to this. Therefore, this one, no, so this parallel which is having some distance is d. So what is the moment of inertia of this one now? Moment of inertia of this we can be written as, so moment of inertia of the center of gravity plus total mass of this object, no, and the distance between these two objects, no, is nothing but a d. So d square, so will be your moment of inertia of any axis which is taken as parallel to your Ig, right? So this formula is very important, no. So we have lot of applications based on this one. No? So we'll write down one simple one, no, graph here, no. Therefore the graphical representation. So the moment of inertia and with respect to the d. So if d is equals to 0, if d is equals 0, therefore here Ig will be there, no. So it is constant, therefore here it will be there. So then as distance is changing, it is like a parabolic, no. So here there is a variation of this graph, it will be like this. Clear? The moment of inertia, so with respect to the distance on a parallel axis theorem can be taken as like this now. And one more small formula we can rewrite it as onto this one. No? What is the moment of inertia here? We written, no? We written here. So I, therefore I is equals to Ig plus m into d square. So I we can rewrite it as like a in terms of radius of gyration, no? That is nothing but a mk square. So what will be the radius of gyration for the axis of this one? No? So therefore m kg square plus m into d square. Therefore m taken common, now cancel it onto this. So radius of gyration for our parallel axis will be equal to radius of gyration of an axis passing through the center of gravity plus d square, right? So in this way, so we can use this parallel axis theorem to calculate the radius of gyration also. Next, one more important theorem, that is nothing but a perpendicular axis theorem. Perpendicular axis theorem. So what is a perpendicular axis theorem now? So therefore this perpendicular axis theorem can be applicable for only plane objects. No, it's a planar object only. This theorem can be applicable, no, for two-dimensional object, I mean three-dimensional objects and one-dimensional objects. Perpendicular axis theorem is not applicable, no. So therefore it will be applicable for only plane objects like a two-dimensional objects now. Clear? So here there will be one sheet is there, no. So we'll take it as like one moment of inertia for this one, no. along this one now, therefore Ix, right? So therefore we can take it as like a, therefore Iy. So now we'll select one Iz. This is your Iz now. Clear? Now this Iz which is there now, therefore this is perpendicular to this x axis now, and this Iz is perpendicular to y axis onto this. So what you can write it now, therefore Iz is equals to Ix plus Iy. So in this way we can calculate. So we have to take it as these three are perpendicular onto this one. Clear? So this is nothing but our perpendicular axis theorem, which can be applicable for only planar objects now. Parallel axis theorem, most important now, it can be applicable for all the devices now, one dimensional object, two dimensional object and three dimensional object now. So like our continuous mass distribution now, how to calculate the moment of inertia. If it is like a point mass distributions now, we already calculated in first part of this one now, right? So for continuous mass distribution now, for continuous, so mass distribution, how to calculate the moment of inertia, right? So here moment of inertia for continuous mass distribution, integral, so therefore r square into dm. So this it will be your moment of inertia formula for this one. For a small amount of mass, we have to calculate it and we have to integrate it. We will see one application now, very simple application. Let us take moment of inertia of a uniform rod of mass m and length is L. So we want to calculate moment of inertia of a uniform rod, like a uniform rod of mass m and length is L. Uniform rod means what? This is one rod is there. This total mass is m and total length is L now. Now we want to rotate it like this. So where we want to rotate now? So here moment of inertia, this rod is there, moment of inertia passing through any one of the end of your rod perpendicular to the length now, right? We want to rotate like this. For this one now, what we are going to do? We are going to select one through this one, any one of this edge now. For this one now, I am going to consider one small amount of dm of thickness is dx. So which is at a distance is x distance from our axis of rotation now. So then we will rewrite it as, so it is a uniform rod. Uniform rod means what? Mass per unit length no, it is constant. You can take it as like a dm by therefore dx. Clear? So therefore here dm you can rewrite it as dm is nothing but a mass per unit length into dx. Let us substitute here now. What will be the moment of inertia here now? Integral. At what distance here now? X square. What is the dm now? Therefore m by L into dx. So what is the limits now? It is started from 0. So how much distance it will be? So 0 to L here. So now we will simplify this one now. Therefore here m by L is constant now. M by L is taken out, integral x square dx into 0 to L. How much it will be? M by L into therefore x cube by 3. So 0 to L. So you can write it as m by L into L cube by 3. Therefore this is 2. So moment of inertia of this rod ml square by 3. What is the moment of inertia of this rod? No, that is nothing but a ml square by 3 now. Clear? In this way we can calculate a moment of inertia of a uniform rod of mass m and length is L, axis passing through any one of its end perpendicular to the length of this one now. Clear? So now we got it as moment of inertia of a rod, uniform rod. Moment of inertia of a uniform rod of an axis passing through this one now, that is nothing but a I is equals to ml square by 3. Now we want to calculate what will be the moment of inertia of an axis passing through at the center of this one. This it will be like a IG, center, exactly midpoint. Therefore we want to rotate like this. Yes, we want to rotate exactly at the midpoint onto this. So here this is nothing but like our IG, axis passing through the center. That means this distance is nothing but a L by 2. We can use parallel axis theorem. Both are parallel onto this. Now you can write down I is equals to Ig plus m into d square. I is how much now? Therefore, ml square by 3 is equals to Ig plus m into L by 2 whole square. Why? Distance is d is nothing but L by 2. So, ml square by 4 taken here now. ml square by 3, therefore ml square by 4, it will be equal to Ig. How much it will be? LCM 4 and 3. So, therefore, here Ig you can write down ml square by 12. Clear? So, moment of inertia of an axis passing through the center of a uniform rod, it will be nothing but ml square by 12. Clear? So, in this way, you can calculate the moment of inertia of an axis passing through the center of this. They may ask you what will be the radius of gyration for this one. No? So, very simple onto this. Therefore, what will be the radius of gyration for this one? No? It is k, it is a root of, therefore, L by root 3 will be the radius of gyration for this. What will be the radius of gyration for this one now? Kg, therefore, divided by m, therefore, L by root 12. So, 12 means L by 2 root 3 will be your radius of gyration here. Clear? So, this is on uniform rod now. There is a like a non-uniform rods also will be there. So, we can calculate moment of inertia in the same way. Let us see one simple question, right? So, here what will be the moment of inertia of non-uniform rod? How it is varying now? So, therefore, linear mass density, therefore, lambda, that is nothing but a, so here it will be right varying like this, therefore, ax plus b, or we can write down like a easy calculation, 2x plus 3 of length, right, of mass m and length is L. We want to calculate moment of inertia of a non-uniform rod whose linear mass density is nothing but 2x plus 3, of total mass is m and length is L, axis passing through any one of its end, right. So, axis of rotation where it is now, it is passing through, so any end, any one of the end. Therefore, we can visualize this one, no? Therefore, as the distance is increasing, linear mass density is also increasing because 2x plus 3. So, that means how the rods looks like now, the rod it is looks like this now, clear. So, somewhere it will be changing onto this, clear. So, we want to calculate the moment of inertia like this now. For this one now, what we want to do? So, we want to select one small amount of part of this one now, that is nothing but a small dm. So, it is dx which is at a distance is x now, clear. So, therefore, we know that dm by dx, this is linear mass density, that is nothing but a 2x plus 3. So, dm you can write down, so 2x plus 3 into dx. Again, we can calculate the moment of inertia, right. So, here I is equals to integral, so therefore, x square into dm is nothing but a, so what you can write it now, 2x plus 3 into dx, therefore 0 to total L, length is L. So, how we can rewrite it now? Multiply this 0 to L, therefore 2x cube plus 3x square into dx. Now, you can rewrite it as 2x cube. X cube means nothing but a x to the power of 4 by 4 plus 3x cube by 3. So, total limits nothing but a 0 to L. This will get cancelled. This it is 2, no? Right. What you will get it now? Here x to the power of 4 by 2 plus x cube, 0 to L. So, if it is L is also given like 2 meters or anything, no, then you can substitute very easily and you can get it. Therefore, what you will get it now? Upper limit is nothing but a L to the power of 4 by 2 plus L cube, this 0, 0. Therefore, this it will be your moment of inertia of a non-uniform rod. In this way, you have to calculate the moment of inertia, so of any objects. What is the formula? So, integral, So I is equals to, that is nothing but a r square into dm. So major important is calculating the dm. So is only most important, no. So and the limits, rest of other things nothing but a just mathematics, no. So you should be thorough in the slightly integration concepts. Right, students, so we'll study moment of inertia of a ring, right? So one ring now. Therefore, here moment of inertia of a ring. So ring, here we know that moment of inertia, this is a ring of mass m, uniform ring, no, of radius is r. So we will calculate moment of inertia of a different situations, no. So ring, this is, suppose this is a ring, so we want to rotate it like this. You are understanding? So rotate it like this. Clear? So therefore, here an axis of rotation passing through the center of this one, right? So what will be the moment of inertia? Moment of inertia is nothing but a mr square. So will be your moment of inertia. How I got this one now? Again, you have to use our integration method, no? So then you can solve it. These derivations, all these derivations, no, not required. So mostly applicative problems only is important, no. So slightly remember this formula, you can remember, you can get it very easily. So now we will take moment of inertia. So this is axis passing through the center now. Now we will take, this is your ring now. So moment of inertia passing through the along the diagonal of this one now. This is your I2. So diagonal means what you can write it now, here along the x-axis. So this also it will be I and I. So here we want to, we know this moment of inertia, this one now, that is nothing but a passing through the center of this one now. So center, how much you know it now, that is mr square by mr square. This is along the x-axis. That means if you are rotating like this, so or if you are rotating like this, both are same only. So if you are rotating like this and if you are rotating like this, it will be the same. So but this one is how much now? It is nothing but a mr square by 2. So you can use perpendicular axis theorem now. So this is perpendicular to both of this one now. So iz is equals to, so ix plus iy. Iz is nothing but a mr square. So it will be 2 into ix. So therefore ix it will be equal to mr square by 2. That means it will be mr square by 2. This is your moment of inertia of a axis passing through any one of the diagonal. So what will be the radius of gyration here now? What is the radius of gyration? So it is nothing but a r will be your radius of gyration in this one now. So what will be the radius of gyration here now? R by root 2 will be your radius of gyration. Axis passing through the along the diameter. Now, so we'll go for now next one, moment of inertia. So here like this. Therefore, so here we know it, moment of inertia of an axis passing through the center of this one, no? You know it, no? That is nothing but a mr square. Here we have to find it now, moment of inertia of an axis passing through the like a along the tangent and perpendicular to the plane. That means this is your ring, therefore here like this we want to rotate it now. Clear? Here we want to rotate it like this. That means this is an axis of rotation passing through the tangent and perpendicular to the plane. This is a plane perpendicular to the plane. Therefore, axis of rotation passing, it's a tangent perpendicular to the plane. Therefore, you can use parallel axis theorem now. So this is your Ig. So this is your R, is a perpendicular distance. This it will become like a Ig. So you can use parallel axis theorem, that is nothing but a Ig mr square. So this total mass is m and it is also m into r square. Therefore, it is nothing but a 2mr square will be your moment of inertia of an axis passing through the tangent and perpendicular to the plane. And next one, right. Now we'll take one more ring now. Therefore, here it is a ring. So, okay, we'll see. Now, here we want to rotate this one now, a tangent and parallel to the plane. That means we want to rotate like this here. You understand? We want to rotate like this. Clear? Na? So that means we can take it as this is your parallel, this is nothing but a Ig. This is along the diagonal, no? That is nothing but this is a formula. along the diameter no, therefore it is mr square by 2. So this is also is nothing but a r. So what will be the moment of inertia? Again parallel axis theorem no. So parallel axis theorem, what you can write it no? I is equals to ig mr square by 2 plus therefore mr square. So what you will get it now? So therefore it will be it will be equal to, so 3 mr square by 2. This is your, so moment of inertia. What is the radius of gyration here now? Root 3 by root 2 into r. Therefore root 3 by 2 into r. This is your radius of gyration. Here what is the radius of gyration here now? Radius of gyration is nothing but a root 2 into r will be your radius of gyration. This is for your ring. Clear? So this is along the ring no. Now similarly exactly the same way for a disc no, right? So disc, this is a uniform disc of mass m and radius is r. So here this is one disc here no, this is a disc. So what will be the moment of inertia here now? I'll go slightly faster because exactly the same. So I is equals to mr square by 2. So how I got it now? Again you have to derive it. So for a derivation is not required for your competitive level no. So right. Now what will be your radius of gyration now? R by root 2. This is your radius of gyration now. Now we will take one more disc here now. Therefore this is your IG. Now this is what? Axis passing through the along the tangent perpendicular to the plane. Therefore here IG is nothing but a mr square by 2. So moment of inertia, parallel axis theorem, therefore mr square by 2 plus mr square. Therefore 3 by 2 mr square will be your moment of inertia, right? What is the radius of gyration here now? Radius of gyration is nothing but a root 3 by 2 into r. This is your radius of gyration. Now so along the diameter, again the same thing, both are same. Here this you know mr square, therefore mr square by 2, it will be 2 times of your ix. Therefore ix it will be equal to mr square by 4. What is your radius of gyration now? R by 2 will be your radius of gyration. Now we'll see. So here there is a disc is then no. Here therefore here is a tangent. Now we can take it as one tangent. This is your I, this is your IG, mr square by 4. Parallel axis theorem again, mr square by 4 plus mr square. Therefore 5 by 4 mr square will be your answer, right? We'll calculate the moment of inertia of a solid cylinder and cylindrical shell. Clear? So solid cylinder means what? Solid cylinder is nothing but if you cut it no, so right, therefore it will gives us like a disc. That means if you arrange all the discs in one order no, it will form like a solid cylinder no. Similarly cylindrical shell means what? If you arrange all the identical rings no, it will form like a cylindrical shell. That means, so solid cylinder means you can remember like a disc. Cylindrical shell means you can remember like a ring. Exactly the same only. So here solid cylinder. Now right, here what will be the moment of inertia? Moment of inertia for the disc no, therefore mr square by 2. Therefore here this it will be your I. So what you can get it now? Here this is your r. I is equals to, so this it will be your Ig, so mr square by 2 plus mr square. Therefore 3 by 2 mr square will be your moment of inertia of an axis passing through along the tangent along the line. Similarly here, right, so here therefore it is nothing but like a rings, no. So moment of inertia of this one is how much, no, mr square. Clear? So here now of an axis passing through this one, no. So how much it will be? This it will be your r. Now I is equals to mr square plus mr square. Therefore 2mr square will be your moment of inertia of this one. Clear? Now therefore here cylindrical, okay, one more thing, no, one more important here, right? Let us see, can you tell me which one will be having more moment of inertia if the masses and radius are same? Therefore here cylindrical shell means it is a hollow part is there, no, it is solid part is there. So solid part is mr square by 2, hollow part is mr square, no. Therefore moment of inertia of the hollow part, hollow, it will be greater than your solid part, right? So provided that mass and radius should be the same, that means hollow objects, no, rotation it will be slightly difficult. Solid objects, no, rotation can be slightly easy onto this. Moment of inertia for hollow part, no, slightly heavier onto this. Now similarly solid sphere and spherical shell. So spherical shell, hollow sphere, we can write it now. Therefore solid sphere means you know already the full material it will be present, no, it will be exactly like a sphere, but it will be fully material it will be present now. What will be the moment of inertia? Solid sphere, so moment of inertia it will be equal to 2 by 5 mr square, but hollow sphere is there, no, hollow sphere. So therefore here moment of inertia it will be equal to 2 by 3 mr square, right? So here shell 2 by 3 means 0.6, no, 0.4. Again hollow spherical shell, no, therefore moment of inertia will be larger. So you can remember onto this, right? Now moment of inertia of an axis passing through along the tangent, this tangent, no, therefore you can use parallel axis theorem again. Therefore Ig is nothing but 2 by 5 mr square plus mr square. How much it will be? So 7 by 5 mr square will be your moment of inertia on this. Clear? Here also therefore tangent moment of inertia Ig, this is Ig because passing through the center, no, therefore 2 by 3 mr square plus mr square. How much it will be now? So 5 by 3 mr square. This it will be your moment of inertia of the sphere, no. Right students, like this we can calculate the moment of inertia of the different bodies, no. So we'll see like a third part of this one, no. So we'll do fully all these applications or by using of all these one, no, different combinations and different questions, no, we will solve like a full part of this one, no. So thank you for watching. Please subscribe to my channel now.